All right, guys. Hello and welcome to this session. So in this session, we'll be looking at anything that you want really, because the actual session that we were supposed to have, we did have on Sunday. So this is really just a formality for students who did request me to have a session today. So that's why we're having one. So just let me know what you guys want to discuss. We can discuss that. You guys can also go through this revision video, which is also there on the channel. So these were some of the things that we were discussing last time out. So yeah, it's really the floor is your guys. Whatever you want to do, we'll do. All right, first let's do it like this. First, let's look at these three chapters and think about any problems you guys might have with these. First, throw these at me. Physical quantities, kinematics, and dynamics. What do you guys want to discuss regarding these? Anything, guys? Formulas I don't get percentage uncertainty and how to turn it into absolute. Well, that's really easy. So the idea about percentage uncertainties is that you use them whenever you have something being multiplied or divided. Let's take a formula that we were just looking at moments ago in another class, which is this, right? The volume of a cylinder. So V equals pi d square h over 4. Whenever you have things which are being multiplied or divided, the percentage uncertainty in whatever you are calculating. So the percentage uncertainty in V in this case is going to be the percentage uncertainty in D plus the percentage uncertainty in F, in H. So whatever you're multiplying or dividing, their percentage uncertainties are added. It doesn't make a difference if something is being multiplied or divided. Even if this formula was pi d square over 4h, even then this would be the same. But because d here is raised to a power 2, its percentage uncertainty would also be multiplied by this power. All right. So this is the idea of percentage uncertainty. Graphs of kinematics. All right. So for graphs of kinematics, I think we also have a few questions down below. The idea is that whenever you have a graph related to kinematics, there are these three steps you should always take. First step, and this may seem really basic, but the first step is to really identify what type of graph you have. Is it a distance time? Is it a displacement time? Is it a speed time? Is it a velocity time graph? First step is to identify what type of graph this is. The next one is to basically recall its features. Like what can the gradient of this graph or what could be the area under this graph used to, what could that be used to calculate? And the third one is then to actually solve whatever the parts examiner has set out for you to do. So for example, if I am provided a velocity time graph, right? First off, I recall that the gradient of a velocity time graph is acceleration, and the area of a velocity time graph, again, this is velocity, so the area is displacement. Once I know this is when I will then start to go on to the questions, right? And then for the graph shapes, obviously you must have a really good grip on graphs for AS. So let me show you some of the kinematics graph shapes just to quickly refresh your memories. For example, if I have a displacement time graph, which looks like this, displacement time. So you can see that this graph is progressively getting steeper. So this means gradient is increasing, and gradient in this case is velocity, so its velocity is increasing. Or the other way around, it's again getting steeper. So if it's getting steeper, so the gradient is really getting more negative. And this is really the case where an object is moving with increasing velocity away from the origin. So if this is where it is at the origin, it's moving with increasing velocity either away like this or away like this. So these are some ideas about the graphs. So you must know what each graph shape represents. All right. Similarly, this is decreasing velocity from the origin. So it's going away, but it's sort of slowing down, right? So that's what this graph looks like. Object moving with increasing velocity towards the origin. So, right, these are just different types of graphs. And again, I don't want to explain this in a lot of detail to a lot of the students because it's possible that you guys have studied this a bit differently. Every teacher has a slightly different way of teaching kinematics class. This is one, right? So yeah, so that's what this is. What else, guys? So we're done with kinematics graph. Anything related to dynamics? Mass flow rate. Can you please explain the effect of mass on acceleration? I don't get how it doesn't affect in free fall, but doesn't F equals to ma suggest that they're inversely proportional? Not at all. F equals to ma basically suggests that mass and acceleration are inversely proportional for the same force. So if I apply the same force on two bodies, if one has more mass, then the same force will cause a lesser acceleration on this. But the idea in terminal velocity in free fall, when we talk about an object falling, is that whatever happens to the force happens to the acceleration. If I just show you another diagram here, really quickly. So if I'm talking about a parachutist who is falling in air, initially when he is dropped, there is no force acting on him except his own weight, right? So if it's dropped from rest, the idea is that all you expected to know in AS regarding your resistive forces, such as drag and air resistance, is that it varies with speed. So if there is no speed at this moment, the idea is there is also no air resistance and it just falls with acceleration due to gravity. But as the speed increases, because as he accelerates, the air resistance also starts to go up, and that's in this direction. So if you look at it, he's going down, but air resistance is acting up. So in this case, if I write out Newton's second law, so resultant force is mass minus acceleration. Resultant force is mass times acceleration. In this case, it's weight minus air resistance, which is equal to mass times acceleration. So the resultant force is now reduced because air resistance has come into the mix. So because your resultant force goes down, your acceleration also goes down. All right. But acceleration going down does not mean it's decelerating. It means it's accelerating, but it's accelerating at a decreasing rate, right? So the speed keeps going up still because it's still accelerating, and the air resistance keeps increasing until it equals the weight, at which point resultant force becomes zero, and that's why acceleration becomes zero, and terminal velocity is reached. All right. What else, guys? Nothing else related to dynamics. How about mass flow rate? The cases where you have mass given as, for example, kgs per second or something like that. Let's try to look at this one. So with mass flow rate, I was talking about questions like these. Right, I'm pretty sure like 90% of you guys remember seeing this question at least. So it says that show over a time of 1.6 seconds, the mass of water hitting the wall is 1.2 kg. The easy way to do this for MCQs as well as for structured questions is to just memorize this formula for such cases, which is that the mass flow rate is given by this expression rho AV, density times cross-sectional area times velocity. And in such cases, if you talk about the resultant force, which is delta mv over delta t, So basically delta m over delta t is this thing. And if you just multiply with another v, so this just becomes rho a v squared. Right, this formula is really useful. What is mass flow rate? Mass flow rate is basically used in cases where the mass is changing, but the object is moving at constant velocity. So if I just give you some examples. So for example, if a rocket is taking off and it's releasing exhaust gases, right? So the mass is changing with time. It's expelling masses constantly. Similarly, in this case, if you look at it, there was this mass of water which is continuously striking this wall. So there's a mass flow rate associated with this. Because you have density, you have cross-sectional area, you have velocity, you can find the mass flow rate, as I did here, turned out to be this. Now, because mass flow rate is really delta m over delta t, and they want me to show in a time of 1.6 seconds, this mass flows. So if I have this per second, I just multiply it by the time in seconds, and I get the mass is 1.2 kg. Again, this is stuff that I've already done, so I don't want to waste a lot of time here. So it's up to you what you guys want to ask. Anything else related to dynamics? How about elastic and inelastic collisions? I also recently uploaded a video on that. Also, this is related to percentage uncertainties, whoever was asking. We had to show the percentage uncertainty in alpha, so we make alpha the subject. And then according to the formula here, we add those percentage uncertainties. This is how you find the absolute uncertainty. Once you found the percentage uncertainty, you find alpha, and then you just take this percentage of the actual value, which turns out to be this. And to give you answer to an appropriate number of significant figures, what you do is first you write your, what do you call it? Your absolute uncertainty to 1SF, and whatever number places these are, whatever decimal places these are, you write your actual value correct to this. So for example, if I look at this, this is 0.401. 1SF, this is 0.4. Because this is one decimal place, this value should also be one decimal place. So this turns out to be 2.7 then. When an object hits and bounces back, do we use the same method as in the elastic video? If you are asked to calculate the changes in momentum, it's different. What is there in that video is basically how you find relative speeds of approach and separation. Both of those are different. If, for example, if something collides with a certain object and you want to find change in momentum, then you must use the sign convention. For example, if I have an object like this, let me give you a really simple example really quickly. Let's say this is an object. So this goes on, this collides with the wall. Let's say this is has a mass of 2 kg, collides with 8 meters per second, and then rebounds with 6 meters per second. And somebody tells me to find the change in momentum. So find delta P. In this case, because momentum is a vector quantity, I need to work with velocities. So I need to specify my sign convention. I need to say that velocities to the right are positive, velocities to the left are negative. So when I use mv minus mu here, obviously it would be 2 times the final velocity, which is 6. But because this is to the left, I'll take this as a negative 6 minus 2, and u was to the right, so it was positive 8. So that's how you do this. All right. So that's how this is calculated. And then we did this one question on projectile motion. I think this was a slightly conceptual question, which we did then. Again, you can watch this from the YouTube video. We also did something on 2D momentum because some people have problems with that. 2mc plus 2mc what? It would basically be an 2 times this thing. So it would be 2 times 6 plus 2 times 8 in a way with the minus sign, right? So yeah. So 2 times 6, 12, and 2 times 8 is 16, so 28. YouTube. You guys should have done this before the video, before today, so that we don't waste a lot of time here. Because this one is just a formality. Because some people ask me to do this, that's why I'm doing this. If you guys have like any problems, also if you have like a past paper question in mind, you want me to do that, you can also do that. Like I'm totally, I don't know what else I could probably do for you guys. Because towards the end, there's also this guest paper that I did. I don't know if you guys know about this. All these questions which I feel like could come in some way. Yeah, Hannah, just tell me the reference and just tell me the part. I'll pick this out. I have physics P5 and a physics P2, and I have math P3 a few hours ago. What can I do for last minute revision? I guess you could, I mean, I don't know how many minutes you have, honestly, but I feel like if you do March 24, that's really nice. And then you can watch my video to confirm your solution. I mean, that's the best thing you could do, provided you have enough time. Right? I honestly, some people ask me whether I should just go through the notes. So I guess there is no, in my opinion, there is no better revision than just doing a paper. In terms of revision, again, now this is slightly, it's going to be different for everybody, but what you can do is, for example, if you studied in a college or in a tuition center, whatever, you can go through whatever mistakes you did and you can just consciously keep those in mind so that you don't repeat them. Should I solve topicals? No, you should not. Not really. If you feel like you are really lacking in a certain topic, then I think you should. But otherwise, yearlies is the way to go. Question 3 from Feb March 2023, paper 22. All right, so you sent an image. All right, that's nice. We did exactly this one in the session. Let me show you. Let's see, let's see, let's see. This is the one, right? Hannah? So we didn't do the last two parts, but I did verbally explain them, and you can also find them in the video. I think the thing you're asking is what? All right, so the idea here is this. If I move this weight closer to the beam, so you can see that at this position, and also this is things that you think of when you do this entire calculation. With this box now here, this distance has reduced, right? And because this distance has reduced, what you used in a previous part of the calculation is that both of these are producing clockwise moments. So the clockwise moments go down. And for this to still be in equilibrium, the anti-clockwise must also go down so that it's still equal to the clockwise moment. Here, the anti-clockwise moment was produced by this component of the tension, right? So basically the tension has to go down. So if this tension goes down, then these horizontal components, they also go down. All right. So that's the reasoning here. Because because this goes down, and again, this is just a component of this tension. So in general, tension goes down. So it's horizontal component here, which by the equilibrium of forces is equal to this force. Rightward force equals leftward force. So both of these go down. Okay. What else, guys? Any other questions? You can throw at me. We can do it now. Hmm. 17 sine, 17 cos. Sine is the vertical one, That's what we did in this calculation, and cos is the horizontal one. Often, do keep in mind that the questions which do come in regarding moments, the first few parts always require you to use this equation, this condition of equilibrium, that resultant moment is zero, and the next few parts use this one. So for example, the question that Hannah just sent, and this is also discussed in the video. The first one, it did tell us to take moments about end A and calculate the weight. Now, because this was in equilibrium, we use this idea that the resultant moment is zero, so clockwise equals anti-clockwise moment. And then to find this force, which the hinge exerts on the beam, I use the next condition, which is resultant force equals to zero. So for resultant force being equal to zero, leftwards and rightwards force must also be zero. If there is this 17 cos 50, which is pulling this beam to the right, there must be the 17 cos 50, the same magnitude, but towards the left to keep it in equilibrium. This is always how you have questions related to, what do you call it? Questions related to turning effects. Why are they both coming down though? Who's coming down? These two. I mean, these two are just weights. One of these is the weight of this uniform beam AB, which is here. This is another block which is placed, that's here. Yes, in my opinion, upthrust is going to be there. There have hardly been papers where upthrust has not been asked at all. I mean, I am actually lost for words to think of a paper where upthrust has not been asked. It's been asked almost every year, every session. Know the ones attached to the string above. This is the tension. Tension is always marked away from the object being considered. This is the angle. So I resolve it into the cos, the component with the angle, and the other one is sine. Ignore viscosity. It's not in your syllabus. You should just know what viscous drag is. A question on upthrust and polarization. Mahi, did you watch the video? Because I did do one there. What about Doppler? This was the equation. A Doppler question. Sure. Let's see. I probably have an older AS paper here. Actually, let's see. A Doppler question. I mean, I guess this is a good question. No, you should not leave internal resistance at all. Who gave you that idea? Never leave anything. Let me just put things into contrast for you. There was this one topic on O-level physics which had never been asked. Never. I mean, in the 15 years of paper that I've, not even 15, I mean, probably like in maybe even in 20 years of papers, what I had never seen, that just came in the most recent O-level physics paper. So what do you think has the least chance of coming in? That does come in. So don't leave out anything. So 8A, I think this is pretty easy. I also explained a question really similar to this last time out. So by reference to the direction of propagation of energy, explain what is meant by a longitudinal wave. Easy. So vibration, so direction of vibration of particles is parallel to direction of propagation of energy. Guys, do I need to do part B? Can anybody just really do it quickly? Off topic, but what would be the phase difference between a point on node and an antinode? All right, so the idea here with stationary waves, if you're asking about that, Aisha, so the idea is that when you have a loop, so any place between two nodes in a stationary wave, they are all in phase. And adjacent loops are out of phase, 180 degrees out of phase. All right. So we talk about points like that. We talk about them with respect to loops. How do phase difference work? What's the question? Guys, what are we getting for this? There is a method. When you are supposed to find the phase difference, or really two methods to do it. For example, if you have to find them from graphs, if you're thinking about if you're thinking about a graph, let's say the displacement time graph. Actually, all right, first let's do this, then I'll take you to a question which talks about phase difference. All right, let's first do this. Guys, what's the answer to this one? Frequency is 800 hertz, right? So I can find the time period, whatever this is. I'm asked for the time base setting. So I know that the time period, whatever this is the time base times the horizontal divisions, right? So time, whatever that turns out to be, 1 over 800 equals to time base, what I want to find, times horizontal divisions. So this is how many centimeters? So one full wave is this, right? So I can see this is 1, 2, and 2.5. So horizontal divisions in this case would be 2.5. All right. Okay, we can go on to electricity, no problems. Guys, if you don't do this, you will be in trouble tomorrow. So at least do this and let me know if this is working out. All right. So that's how you find the time base. All right. Next one, intensity of sound at distance from the car horn is given by this expression, I equals K over R squared. K is a constant. 4.2 shows the car in B on a road. All right. An observer starts at point O. Initially, the car is parked at point X, which is 120 meters away from point O. The car then moves directly towards the observer and stops at point Y, a distance of 30 meters from O. The car continuously emits sound when the car is moving between X and Y. Sound wave at O has amplitude this. Sound wave at Y has amplitude this. Calculate the ratio AY over AX. Again, whenever you see this word intensity, your mind should already be going towards this relationship. So if I want to find out the ratios of intensity, one way I could rewrite this equation is I can say Iy over Ix by this relationship would be AY over AX squared. So if I want AY over AX as a ratio, so this is the root of IY over IX. Now, how do I find IY over IX is through the formula which was given above, right? So at Y, so what do we have to do? So at Y, the distance is 30 and at X, the distance is 120, right? So distance, but again, it's K over R squared. So intensity is in itself K over R squared. So this is K over 30 squared for Y, and it's going to be K over 120 squared for X, right? So let me just write this here. So K over 30 square for Y and K over 120 square for X, and this is all under the root. So K's cancel out, and this would become 120 square over 30 square under the root. So I can write it as 120 over 30 squared and under the root. This should be just 4. Please make sure you do have a good grip on these questions related to proportions. Right, the first mark was just for identifying this. Then if you look at the relationship above, that was K over R squared. So for Y, the distance was 30, so it becomes K over 30 squared, and then it becomes K over 120 squared. If you don't want to do this, it's totally up to you. You just need to then see that K's cancel out, and then you can plug all of this into your calculator and you'll get the same answer. Now the Doppler effect part. When the car is parked at X, this frequency of sound from the horn is 800 Hertz, right? So with it parked, with it not moving. As the car moves from X to Y, the maximum change in the detected frequency is 16 Hertz, determined to 2 as a minimum wavelength of sound emitted by the observer. So for the minimum wavelength, if I want my lambda to be as less as possible, obviously my frequency must be as large as possible, right? So for the frequency to be large, it says the maximum change is 16. So it could be 16 plus or 16 minus. In this case, if I want the minimum wavelength, I need the max frequency. So it would be 330 equals 800 plus 16. So 816, right? So then you just find out lambda. Part 2, the maximum speed of the car. So for this, you need to use the Doppler effect formula, which is FO equals FSV over V plus or minus Vs, right? Why does it say max speed? Is because this change was also max. So I'll be thinking of this case where the car is moving towards the observer, right? So in this case, you know, the observed frequency would obviously be larger. It would be 816. What was its actual frequency? 800. V is the speed of sound, which is 330. And because I'm taking the max frequency, this is going to be minus, and this is Vs. And from here, you just make V as the subject of this equation. Done? Guys, do we need to go over any of this? All right. This is also something really important. I've talked about this in the video, that you need to know how to define these terms such as period, wavelength, frequency. Look, for the last part, what I just did here is if I need the max speed of the car. So I've taken this idea that I'm talking about the car moving towards the observer, right? So you know that the frequency would be greater by this value. So it would be 800 plus 16. That's the observed frequency. If I am taking the case where the source is approaching the observer, you know, I take the minus sign in this equation. After this, I just have to plug in values. This is the actual frequency, 800. The speed of sound is 330, and then it's going to be 330 minus Vs. And then you just do some algebra and make Vs the subject of this equation. All right. Okay. I think this question asks about phase difference. So let's have a look at this one. Speed of waves is 20 centimeters per second. Calculate the wavelength of the waves. So first off, note that these graphs are displacement time graphs. Also note this is in millimeters, right? So calculate the wavelength of the waves. So wavelength I can find using f lambda. And both of these waves are the same time period. If you look at this one, this has a time period 0.60 seconds. All right. So if I use lambda over t, so lambda would be Vt, so 20 centimeters per second times 0.60 seconds. So this would give you your wavelength. All right, I think it's going to be 12. Is it 12? This one, are you asking what year is this from? This is 2018 June, paper 21. Yes, you do need to know the derivations for the equation of motion. Previous one was 2017 November, paper 23, question 4. Just a second, guys. All right. Yeah, so we were on this part. Now in this one, it then says determine the phase difference between the two waves. Now for the phase difference, if I look here, I know that the time period is 0.6 seconds. Let's find what's really the time interval between the two. So let's compare peaks. So for example, if I compare peaks, or even easier is here to compare when both of these is 0, right? So both of these are 0 at a time of 0.2 seconds apart. So my small t here is 0.20. So for the phase difference, I'll take how far apart they are as a fraction of the total time period. And I'll multiply, for example, because this says to give the answer in degrees, I'll multiply by 360 degrees. So this here turns out to be 120 degrees. Sometimes you might also be asked to do this given wavelengths. Yes, again, Ranius, that's what I'm just getting to. This could have also been a displacement distance graph, and you could have gotten the wavelength here, right? Exactly the same way that we got time period, you could have gotten the wavelength. So you get the wavelength, and then you see what distance they are apart. So distance over wavelength times this would in that case be your phase difference. So you have both of these formulas. If I just write here, so delta theta is T over capital T times 360 degrees. Or it could be, if I'm calling the distance apart as x divided by the wavelength times 360. So it could either be in terms of wavelength, or it could be in terms of time periods. All right, let's also do this one. Also, by the way, questions like this one are definitely going to be on there tomorrow, which link to that relationship between intensity and amplitude. I hardly remember seeing a question in which this has not been assessed. And I don't expect that to change anytime soon. This is also going to be on the paper tomorrow. Intensity of Q over intensity of P, again, this is what you must be thinking of. So intensity of Q over intensity of P is amplitude of Q over amplitude of P, but with a square on top, right? So for Q, I then look at the amplitude. So the amplitude of Q is 2, right? It's 2, right? Yes. So that's 2. And the amplitude of P Amplitude of P is 3, right? So 2/3, and then you just square this thing. Again, do keep in mind never to give your answer as a fraction. Do convert this to decimal. So whatever 4/9 in decimals turns out to be is going to be your answer here. All right. Two waves superposed as they pass the same point. Use 4.1 to determine the resultant displacement at t equals to 0.45. So at 0.45, which is this, right here. So you can see that for Q, this value is 1. For P, this value is -3. So 1 minus 3 equals -2 mm, which would be the resultant displacement for that part. Will this meeting's recording be provided? Inshallah. But the thing is that it often takes time for the processing to get final, and then I upload this. So it does take some time. But I will try to do it by tonight, inshallah. Speaking of that, A2 recording is now live. Let me download that as well. All right, guys, what next? Waves is also done. Anything regarding waves, diffraction, gratings, Young's double slit, anything of that sort? Anything regarding upthrust, maybe? In upthrust, something that confused me as a student is this idea that the formula rho GV, in that the V is only the volume of the object which is below the liquid, right? Sure, Rania, why not? You guys are just going to tire me out today. Okay, let's do. Let's do this. Can we do a nuclear physics question? What were the formulas for the fringe distance and stuff? This is, by the way, provided in your formula sheet, but it's really this. Lambda equals ax over d. Some people use that variant of the equation where x is the subject. I like this one more. If it's not immersed in the liquid, there would be no upthrust. Simple as that. Also, another question I just remembered, is there was a question on your paper which asked you to explain the origin of the upthrust. How does upthrust come about? Now, this is sort of a gray area in your syllabus, whether the derivation of upthrust is there in the formula, is there in your syllabus or not, but I make students do it anyway, because it does tell you a lot about how upthrust occurs. For example, in this case, why does this cylinder experience an upthrust is because of pressure difference between the faces, between the top and bottom. Right, so the pressure difference, and because the pressure is greater at the bottom face because it increases with depth, it applies an upward force. All right, so always also be wary of this question. Okay, now let's do this one. The cylinder is in equilibrium with it immersed in the oil. So then there you have some description on how this works. So spring balance is used to weigh a cylinder that is immersed in oil. So the spring balance applies some force. Reading on the spring balance is 4.8 Newton. First thing that you have to note is that what the spring balance reads is really this tension in the wire, which is 4.8 Newton. Length of the cylinder is given, cross-sectional area is given, weight of the cylinder is also given. So the other force is this weight, which is 5.3 Newtons. This is 4.8 Newtons. Just by looking at this, you know that for this to be in equilibrium, there must be another upward force. And that should be equal to 5.3 minus 4.8, which should be 0.5 Newton. And you know, because of the next part, that this is because of the upthrust. right? So here I would say that there's an upthrust. And again, as the word shows, upthrust is always upwards. So U here would really be W minus T. So 5.3 minus 4.8 is 0.5 Newton. And then you use rho GV, right? So rho is also, this is something which was assessed once in an MCQ, but rho here is not the density of the solid, it's the density of the liquid. Again, you can only remember this if you remember the derivation. In the formula for liquid pressure, rho GH, that rho is the density of the liquid, which is why here as well you have the density of the liquid, which is what you're supposed to find in this case. So rho here would just be 0.5 over G, which is 9.81, and the volume. So this is 13 cm squared, this is 5 cm. I want my answer in the classic SI units. So I need to convert both of these to meters, right? So if I just stretch this out, 13, 1 meter is 10 to the negative 2 centimeters. So centimeters square would be 10 to the negative 4. And similarly, this is 5 into 10 to the negative 2. All right. So you just plug all of these values in and then you get the density. Rania, happy? We've done one on upthrust as well. What else, guys? No worries. Anything else related to this? How about deformation? Do we want to go through deformation? Order of maxima? Sure. We'll do one like that. Guys, do we want to go through deformation? Personally, I feel like deformation paper 2 is not really all that hard. Deformation P1 is super duper hard. All right, so we have order of maxima questions on diffraction gratings. Sure, all right, first let's get done with everything leading up to electricity and then we will go to electricity. Okay, so what did we just say? Order of maxima questions, right? Order of maxima. All right, let me just open up some notes here. All right. So this is about diffraction gratings, and I personally just do one example of diffraction grating, which is so comprehensive that it covers all the parts which could be possibly asked. So with diffraction gratings, always remember that if the examiner gives you this many slits per millimeter or centimeter, you need to convert that to the slit separation. You do that by doing 1 over D. So D is 1 over N. Then you have the monochromatic light, which when hits the diffraction grating, it basically splits into all of these maxima. Also, the maxima is basically where constructive interference has taken place. And this used to be asked, it's not asked anymore. Why do we use a curved screen? Is that it allows more maxima to be captured versus just a straight screen, right? Because it's curved, so it allows more of those bending of light maxima to be captured. This is the formula n lambda equals d sine theta. N is the order of the maxima, this being the 0th order, both of these being the first order, both of these being the second order maximas, and so on, right? So the counting starts from 0. The central maxima is not the first one, it's the 0th one. Equals d sine theta. Lambda is wavelength, obviously. D is the slit separation, which you find by 1 over n if it's not directly given. Always remember with theta as well that this is the angle between the central and whatever maxima you're talking about. All right. So this is that formula, D equals 1 over n. And now this is that example. So monochromatic light is incident on a diffraction grating having 4,000 lines per centimeter. Again, if it's 4,000 lines per centimeter, so in a meter, it would have 100 times as many, right? So it would be this many lines per meter. lines per meter. And then you just reciprocal this and you get D, right? So 1 over this thing is going to be your D, right? So that's what you found out. So the first part, it says what? All right, so first part, it says find lambda, right? So we know D. The angle of separation of the 0th and the first order. So this means n equals 1, right? So n lambda, n is 1, lambda is what I need to find, D is this, and sine theta is sine 10, and I just rearrange this and find lambda. All right. Next part, angle of the third order maxima. So third order means I need to use n equals to 3, and I just find out theta. Not very difficult. Next one, angle between the first and third order maxima. You can never find the angle between any first or third or second or fourth or second or third maxima, because what the equation gives you, as we just talked about, is the angle from the central maxima. So you find the angle of the third one, you were given the angle of the first one, so you subtract the two to get the angle in between. Another common question which is often asked is the angle between both of this many maxima. So the idea is this, that there's a certain aspect of symmetry here. If this angle that the first order maxima has is θ1, then on the other side, this is also going to be θ1. So this angle between both of these maxima is going to be 2 times θ1, right? So for example, if this was asking me for the angle between both the third order maxima, it would be twice of this value. Pretty straightforward. Part E is a slightly more tricky part, only if you haven't revised this well enough, which is the highest order of maxima visible on the screen. So if I go back to this, the highest order of maxima visible would be 1, which really bends through an angle like this, and this is captured on the screen. So the implication here being this, that this angle from the central order maxima would be 90 degrees in this case, right? So you need to substitute theta as 90, which, if you know math, makes sine theta is 1, and then you just solve for n, right? But n turns out to be, for example, in this case, it turns out to be 5.76. Always remember that this value of n will always be rounded down, not rounded off. If this is the, for example, if this is the diffraction grating, right? And light went through, and this is where on the screen I had this 5.76 maxima. Logic dictates that the 6th maxima would be somewhere below, but I can't go below. So it would really be the 5th maxima. That's why we round down, we don't round off. All right. So then here the maximum, the greatest order of maxima would not be 6, it would be 5. And then another related part which is asked is the total number of maxima. So as we talked about, you have 5 on this side, 5 on this side, and 1 in the center. So 5 and 5 and 1 makes it 11. So it's the greatest number of maxima times 2 plus 1 for the central order maxima. All right. Then questions like these related to theory are often asked. So what happens to the angle of maxima if wavelength is increased? If wavelength goes up, then your sine theta goes up, so theta also goes up. So the angle basically increases. Can I explain part B? What was part B? Look, angle of the third order maxima, right? So I want to find the angle that the third order maxima makes. If it says third order, this means n equals 3. Everything else I really need, I have. So I just substitute it into the equation, and I want to find this theta 3. Abdur Rahman, does this make sense? Anything else you want me to go over? Okay. Guys, so are we now done with everything before electricity? Because now I want to move on to that. Yes, 1 over n is always the number of lines. If you look at the units, it will let you know whether this is D or whether this is capital N. All right. If it has units of length, if it's meters, so you know this is D. Yeah, 1 over n gives D. If it says this many slits per meter or per centimeter or per millimeter, now it's per something, right? So you should be thinking that I should reciprocal this to get the length D, which is what goes into the equation. All right. Nothing else in waves. Should I now go forward? Electricity now. For part B is the theta between, yes, it's between the central fringe and the maximum. Yes. That's by default what theta from this equation will always give you. Rani, I mean, I want to, but I just want to get done with this, you know. You can take a namaz break and then I'll just publish this onto YouTube. At least I'll try. Can you go through KCL and KVL? Okay. Guys, do make sure. Also, I have a strong feeling that this is going to come on your papers tomorrow. So make sure you guys do know this. Why the resistance of a filament lamp changes the way it changes. Yes, Fazila, I will try. I will try, but it does take some time. So maybe I'm expecting like around 10. Inshallah, this would be uploaded. All right, so why the molecular vibrations increase and that produces the resistance to the flow of electrons. So basically the current does not increase as much as the voltage increases. Right, this I strongly feel that this is going to be on your papers tomorrow. These graphs, how do you explain these? I think that March 24 paper was like the hardest question that I've ever seen on filament lamps. Like not really the part on filament lamps, but the part after, which is on YouTube. Diodes. All right, what did we want to do? We wanted to do what? Is it So this is like pretty baby stuff at this point to you guys. So I'm just scrolling through this, but not scrolling fast enough so you guys can still see what it's about. Yeah, I'm just going on to potentiometers while going on to KCL, KVL. Derivation of these expressions is in your syllabus. Just go through this once, it's very easy. KCL is this. Again, definitions could be asked. So for KCL, whenever a definition is asked, you say sum of currents in equals sum of currents out, but you have to say it's for a junction, right? Kirchhoff's second voltage law, again, you say sum of EMFs equals sum of potential differences, but you say for a closed loop. Then there are these loads of examples here. Guys, do you guys know when to use which power formula? Because you have those like 3-mark questions where you have to analyze the power and how power changes in response to some other change. Okay. Okay. Series parallel. Do you guys also know this? How to find the potential difference between 2 points? Questions like these usually come on your MCQs, but I've also seen cases where it's asked in structured questions. So in a question like this, the examiner will ask you how to find the potential difference between 2 points, any 2 points. And usually it will be like between some potential dividers. So the basic idea as to how to do this is this. You take, using voltage division, you find the voltage of the resistors which are connected to the negative terminals, and you just subtract them. So just ignore method 1 for now. If I talk about 950, what's the voltage dropped across here? I would do 950 over 950 plus 550, right? The sum of the series resistances times 12. This would be the voltage that I have across here. I would do the same thing for the 250. 250 over 250 plus 350 times 12. And those two answers I just subtract. So that's what I've done here in method 2. Right? I do 950 over 950 plus 550 times the EMF, 250 over 250 plus 350 times the EMF, and then I just subtract. Right? So I basically use voltage division here. So this is what you need to remember. For the resistors connected to the negative terminals, you just find their voltages using voltage division, and you subtract. This is a KCL KVL problem, whoever was requesting this. So using KCL KVL, write down an equation for I1, I2, I3. All of this is provided in, all of this in black is provided as a part of the question. So you have I1 flowing in, I2 here, and I3 is here. So you can see sum of currents entering should equal sum of currents leaving. So I would say I1 plus I2 equals I3. Next, loop A, B, E, F, A, B, E, F. So if I write down the equation, obviously I would use KVL here. This is a loop. So sum of EMFs equals sum of potential drops. In this case, what you need to do is you need to acquire a sense. You need to define how the current is going to move. Because I see current moves like this, I'm taking this direction. I1 is also in this direction. I3 is in this direction. And then what you need to do is you need to see that if the current enters the negative terminal of a battery, this is going to be taken as positive. The current here enters E1, this is going to be taken as a positive cell, and because it enters E2, it's going to be taken as negative. So this is going to be E1 minus E2. These are the steps here. So this would be E1 minus E2 equal sum of potential differences. Potential differences are easy to write. I3 times R here, and basically I1 times R here, because I1 is what flows in all of here. All right. All right, what else, guys? Potentiometers, right? That's where we were heading. All right, so for potentiometers, all right, so this is about the power formulas. I have talked about this previously as well in the yearly past paper sessions. Is that when you have to use a power formula, pick one out where only one thing is changing, right? So for example, in this case, I'm told that the resistance of the rheostat goes up. What happens to the power through this one? Can I use VI here? The answer is probably yes, but it's not a sensible move to make because the voltage would also change here, right? As a result of voltage division, and the current would also change. So then I should think of either of these, and both of these will give me the same answer here. If I say resistance goes up, this means the total resistance increases, so current goes down, so power also goes down. I also get the same conclusion by using the other formula. If this resistance goes up by voltage division, this takes up a greater fraction of the voltage. So the voltage across this goes down, and again, power goes down. So just be sensible in whatever formulas you use. All right. So this is the question on potentiometers as well. What's this? This was 6A. So this is easy. So ends of the resistance wire in A are connected to the terminals X, Y in the circuit shown. Cell has an EMF 1.5 volts, internal resistance R. Potential difference between X and Y is 1.2 volts. Now again, in electricity, this is how any good student should be doing the question, is that without even thinking about what the examiner wants, you should be thinking about what you can possibly calculate. I read here that this EMF is 1.5 volts, and out of that 1.5, 1.2 appears here. So I know that the remaining 0.3 volts is basically appearing here, right? Current in the circuit, so I have 1.2 appearing here, and this is the resistance of 3 ohms, right? So I can just use V equals to IR, make I the subject, and the current turns out to be 0.4 amperes, right? Then the internal resistance R, how do you find this out? Again, there are a couple of ways. If you identify that 0.3 volts falls across here, you know the current through here, right? Then you can just use V equals to IR. In that case, if I use V equals to IR, I know this is 0.3, current is 0.4, and I can find out small r, it should be 0.75, right? Or you could use the other case where you take the total resistance approach, that the series resistance, in the case of a series circuit, the total resistance would be the sums. All right, this one is what I want to talk about. So a galvanometer and a cell of EMF E with negligible internal resistance are connected to a circuit in B as shown in 6.2. All right. The resistance wire between X and Y has a length of 2 meters. The galvanometer has a reading of 0 when the connection P is adjusted, so the length XP is 1.4 meters. Determine the EMF E of the cell. So the basic idea behind EMF is this. The basic idea behind a null point usage, a null point method in a galvanometer is this, that the voltage is basically proportional to resistance, and resistance is proportional to length. So we use this idea that voltage is proportional to length. All right. So now if we think about this, we know that according to the practice that we just did, 1.2 volts appears across all of this 2 meters length of wire, right? 1 point, so let me write this here. Let's make a table as we used to in elementary school with unitary method. So I have volts, I have length. So I know 1.2 volts appears across a length of 2 meters, right? You should also know that at the balance point, whatever voltage this is across here, this is balanced out by the EMF. This is why no current flows through here, right? So at 1.4 meters of length, what's going to be the voltage here? Next step is very, very straightforward. Cross multiply. All right. So then you just do this, that 2x equals 1.2 times 1.4, and then you just make x a substitute. All right. Ignore the stuff in red. That's because I didn't read the question properly and I thought we had to calculate this again. Whereas in fact, it was really given in the question above. All right. As a general guide, please do go through the YouTube video regarding potentiometers. It has a lot more detail than what I'm willing to go into right now. Guys, what else? What else, guys? I'm waiting. Let's also. I I just talked about the power formula. Abdul Rahman, I just showed that as well. Guys, come on. I just showed you these things. This is voltage divider, current divider. So for voltage division, if you want to find out the voltage across a certain resistor, that resistor goes in the numerator. The sums of those resistances go in the denominator, and then you just multiply by the EMF. Phase difference concept also we've done. You guys are late. We did that in a lot of detail. Do go through the recording. It's no problem. So voltage divider rule can apply for more than two resistors, but current divider only applies for two. Aisha, wait. I'm doing this, then I'll do that. So current divider, the idea is that if you want the resistance, the current through R1, in this expression, you will take the other resistance. Again, this is something some of you guys might not know, some of you might know. This is a useful rule in circuit analysis. All right, Aisha, are you still here? I'll just go through power really quickly once again. Also, if you're still confused with power, you should go through the March. Was it? Was it March? Anyway, there was some video. If you are an alt subscriber, you'll have like thousands of questions like these on the platform. But I'll just go through how you have to use the power formulas. Where did it go? Yes. So I was going through this idea that if I talk about the power formula, you should use a formula where only one thing is changing at a time. For example, if this is a circuit, if somebody says to me that this resistance of the variable resistor is increased, explain the effect on the power of this fixed resistor. Now, in this case, would I use P equals to VI? And the answer here is no, because the voltage across here is also changing, the current across here is also changing, right? I should now turn my attention to these, and I'll show you how both of these will give me the same conclusion. If the resistance of the rheostat, the variable resistor, goes up, total current would go down. And because P through this is I square R, the current goes down, so power also goes down. Another reasoning is this, that if I think about voltages here, as you were just looking at the voltage division, because this resistance goes up, this resistance will now take up a larger share of the voltage, so the voltage across here goes down. So if voltage goes down, power also goes down. Okay. So yeah, we've done potentiometers as well. We can't use P equals to VI because both of these things are changing, right? Because of voltage division, the voltage would also be changing. And because of the impact of the resistance, I would also be changing. That's why we can't use it. So if both of these are changing, how do you talk about what's more, what's less? No, Aisha, here resistance is changing. Resistance is changing, right? So it won't be the same anymore. We're talking about the impact of power dissipated on the power. We are talking about the impact on the power dissipated by the fixed resistor because of this increase in resistance of the rheostat. Yes, the current would change in that case. All right. I guess some people were asking for the guest paper as well. Let me just. What? Must be somewhere here. Yes, voltage remains the same. Rania, don't do it like this. Just calculate it separately and then do it. Right? Don't try to do it in more symbols than you can handle. If voltage is the same, then current would change because the resistance of these would change, right? Aisha, if you have a question, like a pass with a question, then I think I would be able to explain better in that case. What does the gradient of a variable resistor graph? What's a variable resistor graph? Like a VI graph? Again, if this is the linear portion of the graph, then the gradient is the resistance. But let's say if you are given a graph which goes like this is a VI graph, and you are asked to find the if you are asked to find the resistance of, for example, some component at this value, it's not going to be the gradient. Do keep this in mind. This is a mistake I used to make as a student. Resistance is just the value of the ratio of voltage to current. So what you would actually do here is you would read off the V value, you have the I value, you just do V over I. So the gradient idea only works if you have a straight line graph. If you have a curve and if you're expected to find the resistance, it's just the value of the ratio, V to I. What's the derivation of P equals FV? You guys made me just cover, you guys just made me speed run the entire syllabus. Force, so power is work done over time. Work is force times displacement over time. And because displacement over time is velocity, this is what it is. But sometimes MS says it's internal resistance. Huh? Oh, you're talking about another graph then. You're talking about another graph. You are then talking about this graph. That's not the graph of a variable resistor. I mean, in a way it is. That's the graph of terminal potential difference versus current, which is dictated by this equation. So basically here, this is what you have on your Y, this is what you have on your X. So then this is the Y-intercept, this is the gradient. So this thing right here is E, and this gradient is negative R. March 2022, paper 22, question 6. No worries, guys. March 2022. Uh, March 2022. Okay. Actually, that's the last part, right? For filament, do we just say I increases of brightness? No. You say that because current increases and because of that heating effect, molecular vibrations increase, which basically provide an increase in resistance. So even though voltage increases, current does not increase as much. How does brightness even come into this? Explain. You need to explain why the you will basically be asked to explain the resistance, how the resistance changes, and you'll be asked to explain it. So that's what it would be. Aisha, are you still here? I'm waiting for you to confirm so I can start with this one. All right, Aisha, just a sec. Uh, Guys, come on. Let me just show you. Rania, take a screenshot and then read through this on your own time. It's okay, it happens, Rania. No worries. Just take a screenshot, take a break, and then go through the state. Okay, it happens. Okay, Aisha, let's go on to your question. It's just the last part, right? Okay. No, I'm asking just the last part, right? Nothing else? Okay. So it says the current shown in 6.1 is modified by replacing the original resistance wire with a second resistance wire. The second resistance wire, all right, let me take a screenshot because I need to write here. Okay. So it says the second resistance wire has a greater diameter, right? So it has a greater diameter. So this would also mean, Aisha, that this has a greater cross-sectional area, right? And if it has a greater cross-sectional area, this means that resistance is less. Why? Because of the inverse proportion as dictated by this equation, right? Area goes up, resistance goes down. So resistance is less. There are no other differences between the between the second wire and the original wire. By reference to resistance, state and explain whether the power dissipated by the second wire is more than, less than, or the same as the power dissipated by the original wire. Aisha, I think that you did not read this question properly. He is not connecting this new wire in in series or in parallel to the original wire. He's taking out the old one and putting in the new one. All right, it's a simple case of replacing them. So if resistance goes down, then you know here, let me show you the circuit back again. If I have this one, so again, still 8 volts appears here. Yes, because there are just these two components, the cell and the wire. So all of the 8 volts now appear across the wire, as it was also the case previously. So the same voltage appears here. But because of the change in resistance, current would change. All right. So what I would say here is this. I would say that this wire has a lesser cross-sectional area. Sorry, it has a greater cross-sectional area. And hence a lower resistance. So it says the power dissipated by the second wire. Oh, so it says power. Oh, so I didn't read it properly. So power dissipated. Again, so now let's think about this. So what formulas do we have? Again, but it's somewhat linked to what I was just talking about, which is that I know 8 volts is going to appear here. Current is going to change as compared to what it was previously because the resistance changes, but the voltage is going to be the same. So if I use this one, where I say K P is V square over R, right? Voltage is the same, it did not change. But resistance was less, so power dissipated would be more. All right. This is what I'm going to say. Does this reasoning make sense? Rania, why does resistance increases? Because if temperature increases, the molecules vibrate more and they basically pose more of a hindrance to the flow of electrons. That's why resistance increases. No, I should tell me whether do you get it 100% or not. This was what? This was part C. First, tell me whether you get it 100% or not. Otherwise, we won't go on. Not sort of. The arrows are just trying, it's just me trying to tell you what's happening here. I'm just saying, all right, let's write it out. Okay, let's write it out. So I'll say that as resistance decreases, then by the power formula, then by V square over R, because your denominator has gotten bigger, right? A denominator has gotten smaller. So overall fraction, which is power, so power dissipated increases. Happy, Aisha? Does it make sense now? Okay, this is just me explaining what's happening here. All right, good. Thank you, Rania. I'm glad I could help. Let's go on to part D. Okay, so what's part D? Oh, so this is the one you were talking about. I'm sorry, I'm sorry. I didn't read the question properly. Circuit shown in 6.1 is modified by connecting a second battery of EMF 8 volts and negligible internal resistance in parallel with the original battery and the original resistance. So original resistance wire as shown. By reference to the current in the resistance wire. State and explain whether the addition of the second battery causes the power in the original resistance wire to decrease, increase, or stay the same. So by reference to the current in the resistance wire, right? So now what's going to happen here? Now this is, I should different to what, by the way, what you were talking about, right? What you were talking about was connecting a component in parallel, whereas here you are really connecting a cell in parallel, right? These are cells in parallel. So it's different from what you were talking about. Anyway, so yeah, just give me a sec. Yeah, all right. So current in the resistance wire. Now, if I think about it, no, Aisha, it will definitely come. It will definitely come. I don't even remember a question where this is not coming. Look, don't be afraid of it. Just listen. What I'm going to say is going to make a lot of sense to you if you just pay attention. If I have an EMF cell, right? I have some EMF. I take another EMF and now this is in parallel. By parallel circuit rules, isn't the voltage still the same? Right? The voltage is still the same. Yes. If the voltage is the same across this resistance wire, the current is also going to be the same. Yes. If I think about this equation, V equals to IR, no, it would not add up. It would not add up. See, that's where you're wrong. That's not what would happen. In reality, when you connect cells in parallel, this needs a certain current. Both of these cells would split up the current between them. Let's say if this needed 4 amperes, one cell would provide 2, the other one would provide 2. All right. And in a while, I'll also show you the advantages and disadvantages of connecting cells in parallel and in series. But here, the idea is that the current would not change. Think about it this way, that the voltage or the potential difference is what really dictates how the current is going to be. If the potential difference is the same, the current would also be the same. All right. So if the voltage is the same, the current is the same, so the power dissipated would also be the same. Now I know you might be having some second thoughts about this, but let me show you this thing now. Where is that thing? Where is that thing? Probably, huh. Yes, yes, yes. Okay, this is cells in series. Now look here. The only advantage of connecting cells in series is that the EMF adds up. But then there are some certain disadvantages as well. Just read through these. All right. So there's also some disadvantages here. All right, guys. So yeah, Asha, does this make sense? Then cells in parallel. The disadvantage is that the EMF does not add up here. Voltage is the same. But the idea is that this can supply a greater current. So you are right in a case where, for example, as compared to what the load I had previously, if I put in a greater load, that's not what I'm doing here. I'm working with the same resistance wire, right? So if I have, for example, 10 ohms connected here, and let's say this 10 ohms, so the EMF of all of these is 10 volts, right? All of these is 10 volts. If there was none of these, then that single voltage source would be supplying 1 amperes of current. But now with the 3 of these supplying the same 10 ohm resistor, now the current which it needs, which is 1 ampere, is going to be split. This one is going to provide 1/3, this one is going to provide 1/3, and this one is going to provide 1/3. Does it make sense now? No, there is no such method. Okay. So guys, let's call it a day here. Again, best of luck for your exams. Don't fret too much. Just go through some of these questions, go through the guest paper, go through that YouTube video that I talked about. And yeah, just go through some important questions which are included in those videos. And yeah, just don't fret out too much. Do make sure that you have a good night's sleep. before you go into the paper tomorrow. That's really important, especially before a paper as technical as physics. All right. So thanks, guys, and best of luck. All of us are rooting for you. So we hope you make us proud. All right. So take care, guys. Bye bye.